Hello, you should see my desktop. There's a few people there. Are you seeing the desktop? Do you hear me? Does it seem like everything's working?
Yeah.
Yeah, okay, great. Okay, people are starting to come in. There's only a few people here so far. Okay. More people are joining. Still a few people to go. Okay. We're going to look at more stuff about threads today. We're going to stick with the easier threads, the P threads, the C threads, before we start talking about Java threads. Okay, so we're going to talk for 1 or 2 more days about P threads and get the basic idea of what a thread is, and then we'll switch to Java, which is got a bigger, richer library of things to work with than the P threads does. Okay, now up on the website, we're gonna finish some of the examples in this zip file, and then start to talk about this zip file, something called race conditions, which is a real important idea in threading. So this zip file, I'll download it here. This zip file is the basics of threads, what a thread is, and this file is about one real important problem that comes up when you do a threading program. The problem is called race conditions, and it's something that we have to be really aware of. Okay, so I'm gonna unzip this one and we'll start looking at some examples in it. Nope, that's not what I want. Okay. So here's the examples we've been working with. Now, first, let me ask, has anybody got any questions about these examples? Anybody try anything at home that didn't work, or did anything seem funny or not the way it seemed to be? Does anybody have any questions about these examples, about what we've done so far? Any questions at all? Any questions about what we've done so far with this code? Anything? Okay. All right. So, remember, we did the basic examples of what it means to run 2 threads. Have a program running 2 threads. So we stopped with this example here. This was the example that has 2 functions, but one of the functions is created as a thread, and one of the functions is called as a function. So this program has 2 threads, one thread going through this function and one thread going through this function, which is the main thread. Okay, so that's the last example we did. In the example before that, we launched 2 threads, one in this function and one in this function. And then the main thread just waited for both of those 2 threads. Okay. All right. So now let's look at the next example, what it does. Oh, the next example passes an argument to a thread. Okay, so it's worth looking at how to do this. This is why the threads have this funny parameter void here. See, a thread function takes a pointer to void. Remember, I mentioned in class the other day, a pointer to void is like an object reference in Java. It can point at anything. Okay, so suppose I want to pass this function an integer argument. Okay, so what I pass it is a pointer to void, which happens to be an integer. And then the function's supposed to know what this thing points to, so it casts it back to a pointer to integer and then dereferences it. Okay, so it's just like in Java. If you have an object reference, you need to know what it really points at, and then you cast it to what it really is. So I know what this thing really points at, so I cast it to what it really is, and then I can dereference it. So if I wanted to pass a double pointer, I could. If I wanted to pass a string argument, I could. That makes these functions versatile. They can take one argument of any type. And if I need to pass them 3 or 4 arguments, I stick them in a struct. Or a class. In a case of Java, I would bundle them in an object. So this is very versatile. The function takes an argument, a pointer to anything. Okay, so the function can take a pointer to anything, so you can pass it anything, And since you're the person who wrote the function, you know what that thing is, so you can cast it to what it really is, and then dereference the pointer and get at the thing. The same thing's true about the return value. This function can return anything. It can return a double, it can return an int. Now, it won't return a double, it'll return a pointer to a double. If it wanted to return an int, it really returns a pointer to an int. But the person who wrote the code needs to know what this thing returns, because it's going to return a pointer to void. Pointer to voids can't be used directly. They must be cast to something, and then they can be dereferenced. So the same, it's just very much like Java. An object reference, you can't do much with it unless you cast it to some other kind of reference, and then you can access it. All right. So here, what I'm going to do is I'm going to create an integer for one of the threads, an integer for the other thread. I call the function with a pointer to that integer. See, so I'm using the address of operator. So I call, well, this is actually printing it. Down here is where I create the thread. So this is when I'm going to print the integer just to see what it looks like. Okay. Here, I'm going to create the thread and I'm going to pass it the address of. So that's really a pointer to int. This is pointer to int, but a pointer to int is a subtype of pointer to void. So this function can accept it. So a pointer to int is a pointer to something. So a pointer to int is a pointer to void. Now this function doesn't get a point. Well, it really does get a pointer to int, but it doesn't know that. It has to cast it to pointer to int. It's tricky. It's not much different. It's trickier than object-oriented programming, but it's not much different than it. Yeah, this is just playing around with pointers. Okay, so I'm passing an integer argument, and I pass it as the address of the integer argument, and then I cast that pointer to void back to pointer to int. Okay, so each of these threads gets a different argument. Okay, so that just shows you that the thread, you can pass information into a thread. Okay, now let's just compile it and run it. I'm going to open a command line here. Now, I don't remember if I mentioned this the other day. I was compiling these using that program that came, the CS302 folder. I'm going to compile things differently today. Before, I was compiling things by using this little C compiler. Okay, now I'm going to still use the C compiler, but I'm going to use it a different way. In the C compiler, there's the C compiler. There's a make program, which is a standard part of the C world in Linux, in Linux using make. So I'm going to use make today, just show you how you can use make to compile things. Okay, I have a make file in this folder. The make file tells you how to use it. So I'm going to copy that little thing that says here, you have to call the make file that's in that folder. So so this just gives you a path to that make file. Okay, so I can just copy and paste that here. Okay, now that make file has the instructions for building all the programs that are in this folder. So one thing I can do is go over here and paste that command in there, hit enter, and now everything in that folder gets compiled. Okay, I just compiled everything in that folder. Okay, but sometimes I don't want to compile everything. So make clean will delete everything. Okay, so now here's how I compile just one program. If I type make, if you type make with no parameter, let's look at the make file just real quickly. Here's how you kind of think about this. These guys are called targets. That's a target. That's a target. That's a target. If you don't tell make what target to use, it does all. And all builds up a list of programs to build, and then it switches to this target to build each one. Okay, like when I type make clean, I'm calling this target. So I'm calling the delete function. So I named the delete function remove, so that because on Linux there's a different delete function than on Windows. So we use a variable name to represent the delete command. And then here we can write a delete command that would work on either Windows or Linux. But up here, I'd have to change this to be delete for Windows and RM for Linux. Okay, so these are targets. Okay, now here, if I say make clean, I'm executing the clean target. If I type all, that's the same thing as if I just type make. But I can target one program. So I want to target the for a. Now I don't want to target now. Make, you have to think about how make works. Make says make something for me. I want to compile this program .c, but I don't need to make it. It's already made. What I want to do is I want to make the exe file from that C file. So if I tell it to make this, it's going to come back and say there's nothing to be done because that file exists. What needs to be made is the exe file from it. And it just did. See, it made the exe file. Okay. So you tell make what it should make. You give it the target of what to make. So in this case, I wanted to make that exe file. So I can compile that one exe file. Then if I want to delete it, I can just say make clean, because that'll delete everything. Okay. Or I can just remake it again. Okay. Okay. So that's how you can compile one file at a time this way. You can use the make file to compile the file, and it will it'll compile just what you tell it to. Oh, here's a little quirky thing. I don't even know how to explain this. Let me delete. I'll just delete this. Suppose you say make this without any extension. Okay, if you say this, it'll tell you there's nothing to make. If you say this, it'll make the exe file. What if you just say this? Like on Linux, it's common to not use the exe extension. Okay, if you do that, it kind of makes it, but something fails in the make. Okay, what it used the wrong make command, and I'm not sure why. I actually don't know why that works that way. So you've got to remember to make the right thing. Yeah, it sort of worked here. It did run make, and it tried to compile my program, but it didn't compile it correctly. So, and that's because I didn't give it the right target. I gave it actually a Linux target, not a Windows target. On Linux, the target would be that. That would be the target on Linux, because on Linux, you don't put the .exe extension on executables. But on Windows, the target is with an exe, and then it builds it correctly. Okay, so you would use this command on Windows, and you'd use this command on Linux to build a one program at a time. Okay, all right. Now let me run that program. This is the one that runs with with the threads with parameters. So okay, there's the two threads running. Okay, and notice, remember, the threads got all goofed up. The threads got, yeah, but you can see hello from thread with argument. You know, there's the argument of one of the threads. There's the argument of one of the other threads. Yeah, so they got all messed up. They got all goofed up because they were the threads are running concurrently. If you look at the code, it's the same program as before. The thread prints a little bit, then sleeps, then prints a little bit, then sleeps, and then prints a little bit. And the other thread prints a little bit, then sleeps, prints a little bit, then sleeps. So the order of the execution gets all jumbled up because they're really running at the exact same time. Okay, so you can give the threads, you can pass arguments to a thread. Okay. Now we're gonna see how that works in Java. Java is going to be designed similarly to this, and Java is going to have what we call an interface to the thread. This is called the thread's interface. It has to be very generic because everybody's thread needs to work differently. So how can you have one interface that's generic? This is a typical problem in almost all programming. How do you create generic interfaces? Well, in C, the most generic interface is to take one pointer to void as input and return one pointer to void. That can take one of anything and return one of anything. And the one of anything it takes can be a bundle of things like a strut or an object. Okay, so this is a generic interface. So the thread library says, here's the generic interface that you must use for threads. Java is going to be the same. There's going to be a generic interface to threads that's going to use something kind of like this. And that way the thread library doesn't have to be telling you what to do. The thread library is telling you what to do, but it tells you what to do in a way that lets you do almost anything you want. So the thread library says you must use this interface, but this interface is generic enough that you can pretty much do whatever you want. You can take anything as input and you can return anything, but you're left with this weirdness that you have to do casting. Because the input must be a pointer to void, you must cast it before you use it. And since the return is a pointer to void, when you call one of these, when it returns, you have to cast what it returns also. Okay, so, the return values for threads aren't used very often. Parameters input to threads, because remember, the thread doesn't return to anything. This return value can be gotten by a special function call. The thread doesn't actually return to anything. So we won't show it, but to actually get the return, since the threads are not functions, their return values do not come back to you. You have to ask for them by a special function. Okay, so they're not used anywhere near as much as parameters into the thread. Parameters into threads are really useful. Return values from threads are slightly less useful. Okay. Right. So that's one. So that's just an interesting thing, that you can pass information into a thread. Okay. Well, let's look at another example. Now, this example here is really no different than the ones we've done before. It's just meant to set up example 6, which is an important example. So we're back to two functions that take two threads. Okay, it's two functions, each there'll be a thread in each function. Okay, this function prints A's, this function prints B's. Okay, I'm sorry, this function prints A and this function prints B's. So if you call this function as a thread, the thread prints A, and if you call this function as a thread, the thread prints B. And this thing creates two threads, one in thread 1 and one in thread 2. Okay. Okay. So if we want, we can compile that and run it, but it's exactly what we've seen before. Okay. So well, we'll go ahead. So that would be compiling. So that compiles that one. Okay. And if I want to run that, okay, so it's just a mixture of A's and B's. Okay. There's two threads running. One thread is printing A's, one thread is printing B's. Oh, and I can't remember. I think this thing runs forever. See, did I? Yeah, this one actually runs forever. See, those loops run forever. So it'll just keep printing A's and B's forever. And you can stop it by clicking on the window and then start it again by hitting enter. So if you click on the window, Windows will pause the output for you, and then you restart it by actually hitting any key on the keyboard. So click on it, space. Yeah, I hit space to stop it, but you have to click on the window to pause it. You can see what kind of, you're just getting weird mixtures of A's and B's. The two threads are just outputting one A, each thread's outputting one A at a time or one B at a time. Okay. And they're just getting, this thread will be running on a CPU and it'll manage to get a bunch of A's out. Then this thread might be, the threads might be really running at exactly the same time, or the threads might be alternating. Like maybe once this one's running on a CPU and then it gets paused and this one runs on a CPU. So the ordering of these threads is impossible to guess what it is. And if you look over here, you see all kinds of mixtures of weird mixtures of A's and B's. Okay, right? So Control C will stop that. Okay, that kills the program. Okay, now here's the one that's real interesting. This is nothing different than what we've done before. So this example is almost exactly like the examples we did before. But the interesting one is the next one. Notice that this one's called two threads and two functions. This one's called two threads and one function. What it does is it does it's essentially this program here, where this thread takes a parameter. Instead of there being two threads, there's one function that takes a parameter, and you instantiate the thread once with one parameter and a second time with a second parameter. Now, this is the first time we've seen an example where one thread function is being used to create two threads. That's the new idea. Okay. If you look here, I'm actually going to create as many. Initially, I'm going to create two threads, but I could create 10 threads if I want. So I put the thread creation in a loop here. Notice that I'm creating the same thread over and over again, but it's not the same thread. It's the same thread function. So what I'm doing is every time I call this, I create a new thread control block. The new thread control block represents a new thread, but it points to the same function. So all these threads are executing within this same function. So the function is not the thread. This is a really deep and important idea. Everything we did before kind of made it seem like the thread was the function. That one thread was this function and one thread was that function. And we did that over and over again. One thread was this function, one thread was this function. That's actually misleading. Threads are not functions. Threads are instantiations of functions. It's kind of like the difference between a class and an object. You can take a class like string and you can instantiate lots of different strings from it. Well, here the idea is you can take this function and instantiate many threads from it. And each thread, and so this guy creates threads, instantiates threads out of that function. But each time it doesn't, so that function is not the thread, it's the thread the thread is the thread control block. The thread control block is really the thing that's the thread. Okay. So this is a lot of people don't ever get used to this. They keep thinking that this function over here is one thread and this function over here is another thread. And the next level of thinking is to realize that the thread doesn't really have much to do with the function. The thread can just be created, the thread just represents a start point. Functions represent good starting points. So we tend to start threads at the beginning of a function, but the function is really just being used as a template for creating the thread. Just like a class file is a template for creating an object, this function is a template for creating a thread. And here I can give each instantiation a different parameter. So now every time I instantiate one of these thread functions, I'm going to instantiate it with a slightly different parameter. I'm going to have an array of parameters and give each thread function a different parameter. Here's where I fill the array. Like the first thread's going to get A, the next thread's going to get A plus 1 is B, the next thread's going to get A plus 2, which is C. So the threads get the letters A, B, C, D, and they print them out. Okay. So let me compile this one. So I want to compile. Okay. Now I'm going to run it. Now when I run it, it doesn't look any different. So running it doesn't look any different than the examples we've done before. So it's just going to print out A's and B's. Okay. I think this one runs forever too. Okay. Now, if I go back and change the code, let me print out, let me create 4 threads. Okay. Rebuild the program. Run it again. Now you can see I'm getting mixtures of A's, B's, C's, and D's. Okay, let me switch to Task Manager. We should see 4 threads in this guy now. So here's Task Manager. Here's the program. And let's see, 8 threads, 8 threads. Why 8 threads? Let's see. We're creating 4 threads. We're creating 4. Oh, and there's the main thread. So there really is 5 threads. See, the main thread is just sleeping. So that's 5 threads. So there should be 5. Oh, now it's back down to 5. Those extra threads are there at the beginning. Let me close this. Let me kill this program. Okay. Let me run it again. See, it's got 8 threads for a little while. I think those extra threads maybe they're either something to do with the console output, or there may be threads that are doing something like they might be threads that are zeroing out memory or something like that. They're going to go away in a few seconds, and we'll be down to 5 permanent threads. See how long it takes to get rid of the extra threads. This Windows didn't used to do this. I remember like Windows 7 didn't do this. In Windows 7, these programs would have as many threads as exactly that many threads as we launched. I don't know where these extra threads, I've never seen references to C creating extra threads. Java creates lots of extra threads. You create 1 thread in your Java program, and we'll see later that you could have like 20 threads actually running in your Java program. Java is famous for having lots of extra threads. There's garbage collection thread, there's monitoring threads, there's quite a few extra threads in Java, but that's well known. I've never seen a reference that says what extra threads there are in a C program, because the definition of C does not include threads. The C language is a single thread. The C language was invented before threads existed. So threads are actually not even part of the C language. So a C program should only have 1 thread. So when a C program comes up with 2 threads or 3 threads like these do, I'm sure it's something to do with Windows, I think. And I don't know what those extra threads are doing. I'm going to see if I can, if anybody finds out, let me know. If you can dig up something that says where those extra threads are coming from, I'd be real curious to know what they are, because they weren't there even a couple years ago. They seem to be a Windows 10 kind of thing, something to do with Windows 10, which makes me think they might have to do with with the console window. I have a feeling they have something to do with the console window, because the console window was changed dramatically in Windows 10. This console window in Windows 10 is actually a very different system than there was in Windows 7. Okay, all right. So, but you see, we got 4 threads printing out A, B, C's, and D's, and then there's 1 thread, the main thread, which is just doing nothing. In this program, I have the main thread sleeping. Instead of the main thread waiting on these threads, I made the main thread sleep. So it's actually running. It's running, but constantly it wakes up, sleeps for 1 second, wakes up, sleeps for 1 second, wakes up, sleeps for 1 second. That's as opposed to what the more sophisticated thing would have been have this thread wait on one of these threads, which are going to run forever. These threads run forever. Okay, all right. So now there's 4 CPUs running around this code, which is an odd idea. In this output here, this output is being caused by 4 CPUs all executing within this narrow little range of code. If we go back to our pictures, we have 2 or more CPUs running around in the same little block of code. And they don't bump into each other. Even they might actually read the exact same instruction at the exact same time. They might be stepping through memory in sync with each other, though that's very likely. More than likely, the 4 CPUs are just running through here independently of each other, though there's a very small chance that they're in sync with each other. But what you're supposed to imagine is 4 CPUs are running around in this same little block of code. Okay. Now, I can do some other things to play around here. Let me do something else to play around with this. Like this other picture here, you imagine, what if there's only 1 CPU? Okay, so there's 3 threads, and suppose these 3 threads are all running around in this one little block of code. But since there's 1 CPU, remember, you're supposed to think, well, 1 CPU runs around for a little while in there, then you switch to the other thread control block, which starts you back up in there, but in a different thread. Then after that thread's run for a little while, you go back to this other thread control block, which would put you in the same block of code, but maybe starting at a different place, and you'd run around in here for a little while. And you have to switch between this thread, this thread, this thread, this thread, this thread, and this thread. Now, I can actually do that on Windows. I can create this picture. Now I'll show you how. right now this program is running on it's running 5 threads, but there's 12 CPUs. So for all I know, every one of those threads is on a different CPU. But now go to Task Manager. Here's the program, right click on it, and go to this thing that says Set Infinity. This is a real nice trick you can do. Set Infinity lets you decide what CPU a program is running on. So that tells the program to run on only one CPU, CPU 1, okay? Now, right now, all those threads are running on who knows what CPU. Here, they're going to be all restricted to the same CPU. And let's see if I can get, it's kind of, let's see, you would see the difference in the output if I had more than one monitor. Like right now, notice how you get blocks of A, blocks of D, blocks of A, blocks of C. Notice how they're in blocks. That's pretty much because what's happening is that one thread gets the CPU, then another thread gets the CPU, then another thread gets the CPU, then another thread gets the CPU, and it tends to kind of like go from thread, when one thread owns the CPU, that thread prints out its letter. So you see less interleaving of the letters. Now I'm going to give those 4 threads 2 CPUs. Things get a little bit more jumbled up now. It's kind of hard to see, but things are a little bit more jumbled up because now there's 4 threads running in 2 CPUs. So there's potentially 2 threads running at a time. So now there could be A's and B's mixed up, or B's and C's mixed up, or C's and D's mixed up, but maybe not all 4 letters mixed up, though you can't really quite tell that. Okay. Now, if I go back over here now, I could set affinity. I could actually give that thing 4 CPUs. Now, it can't really make use of more than 4 CPUs. So right now, potentially all 4 threads are running. And if you look, there's a lot more jumbled upness now. You can see A's and B's next to each other with C's and D's next to each other. So right now, okay, it looks more jumbled up. Okay, now go back to 1 CPU. I'll put them on CPU 0. See, notice I'm back to blocks. Okay, so you can kind of see that the behavior is changing. When you see these blocks, you say, well, okay, the reasoning seems to be that only one thread can be running at a time now. The 4 threads are sharing 1 CPU, so only one of them can be running at a time. So when one of them's running, its letter goes out, and then it loses the CPU after a little bit of time, so somebody else's letter goes out. Then it loses the CPU after a little while, and somebody else's letter goes out. Okay. And if I go back and give it now 2 CPUs, it's going to be a little bit more jumbled up. Yeah, see, a little bit more jumbled up, but not a lot more jumbled up. I get a lot more jumbled up when I give it a bunch of CPUs. Here, I'm going to give it 1, 2, 3, 4, 5. I'm giving more CPUs than it needs. I'm giving it like 5 CPUs now. Okay. And things get a lot more jumbled up. Okay. So, we have a little bit of a verification of what these pictures look like. With these experiments like this, we can actually see this behavior happening. And I think that's really important. I think it's important to actually convince yourself that this model, this picture, which models what we think the CPU is doing, is reasonably accurate. Okay. It does kind of help us think about what we see happening over here. Okay. Now let's see what other one. Let's see, okay, let me kill this one. Okay. Now that was multiple threads all running in the same program. Now, okay, now let's do another example. Here's another idea. The main thread starts up. The main thread's going to create a thread. Then the main thread's going to exit. So exit means destroy this thread control block. Create thread creates a thread control block. Exit thread destroys a thread control block. This destroys the main thread's thread control block. Well, what should that do? Well, it depends on the thread library. In some thread libraries, the main thread control block is more important than other thread control blocks. And if the main thread control block ends, all the other thread control blocks are destroyed too. Java works that. No, I'm sorry, Java doesn't work that way. But some libraries work that way. Others take the point of view that that all the threads are equal. Okay. This library takes the point of view that when the main thread control block exits, it's no different than any other thread control block exiting. So what's going to happen is that's going to leave this thread running. So this thread will exit. So there'll be one thread, then there'll be two threads, then they'll be back to one thread, and that one thread will be running down here. Okay, right? So let's run it and see that this is going to. I call this an orphan thread. This, in a sense, this is the child thread of this parent thread, because this thread created the child thread, but then the parent thread exits, and then the child thread gets running by itself. Okay. What we actually should do is put a sleep in here to see that. Okay, let's run this, and then we'll modify it, and we'll see a little bit what's going on. We'll watch what's happening here in the task manager. Okay, so let me build 7. Okay, and then run 7. Okay, now you don't really see anything. That's the child thread running. Okay, so if you go back, okay. See, starting child thread, stopping main thread. So right now, this is the child thread running, and it's going to run forever. Okay, and if we watch this program in Task Manager, unfortunately, if we watch this program in Task Manager, we won't see much. It's got one thread. So let's put a sleep on the parent thread so that we can see when the parent thread dies, just so we can kind of see it happen over here. So what we want to do is go to this program, and here, let the parent's thread sleep for, say, 15 seconds. And then the parent thread will exit. Okay, so the child thread's going to be running, and now what we should see is this program starts up with 2 threads, and 15 seconds later it's down to 1 thread, which would be this one. Now there's this problem of these extra threads that the operating system's throwing in there. I hope that 15 seconds is long enough that the extra thread goes away. But let's see what happens. Let's try this. So we should see 2 threads for 15 seconds, and then the parent thread should just go away, and then you'll see that, but the program will continue running from the child thread. So remake the program. Whoops. Oh, I forgot to include Windows. See, I hadn't used sleep function before. So sleep function is in the Windows.h file. Okay. Notice to see, I got this message that says, in function main, implicit declaration of function sleep. Okay, notice that it's a warning. My program actually compiled, okay, but it'll not run right. So you got to be careful. C is a weird language. You can get warnings when things are really broken. Okay, so it couldn't find the function sleep, but I didn't get an error. I got a warning, which is weird. Okay, So you got to make sure, always pay attention to your warnings in C, because warnings can actually they could be telling you something that means the program is completely messed up, but it'll still supposedly run, but it's not going to run the right way. Okay, so I need to include windows.h to be able to use the Windows sleep function. Okay, so now compile. See, now it compiles fine. Okay, and I'll run it. Whoop. Okay, switch to task manager. Okay, now look, it's got 5 threads at this point. There seems to be 3 extra threads for some reason. Oh, see, it went from 5 to 1, which means that it took longer. Okay, so we needed longer than 15 seconds, it looks like. Okay, so let's try say 20 seconds. Okay, there's 5 threads. It should go 5, 2, 1 if we see it the right way. So I don't know what these other 3 threads are, but we should see it go 5, 2, 1 if we waited long enough. Yeah, went 5, 1. Let's try one more time. Wait 30 seconds. Just oh, wait a minute. Let me try something. Let me just check that I didn't do goof up something. Let me launch it and then kill it right away. Yeah, starting child thread. Yes, it's a starting child thread. Then it should be a bunch of output. At some point, you'll be a message mixed in there saying that the main thread is exiting, but you won't. It'll just get buried in all the A's. Okay. So there's 5 threads. I don't know if we'll see it go from 5 to 2 to 1. Experiments like these are important to do, but they can be annoying because they don't always work quite the way you want them to. Like these 3 extra threads, I have no idea where they came from and what they're doing there, but they're making the experiments hard to do. Yeah, maybe you have to, I don't know how long you have to wait. I don't know what's going on. Unfortunately, those extra threads are making this experiment goofy. Yeah, I don't know where the threads are coming from, and I don't know if there's a way to control them, but they're making this experiment be kind of goofy. Yeah, we should see the program go to 2 threads and then 1 thread. Okay. Yeah, I'm not sure what's going on there. We're sleeping for it should give that should be enough time for those other threads to go away. And then we exit this thread. Okay, notice that by exiting here, we never return. That's actually important. If the main thread returns, and we're going to see this in another example, if the main thread returns, that kills all threads. That's different than a main thread exiting. The reason is that in the C language, there are no threads. And in the C language, by definition, when the main method returns, the program's over with. They can't change that when they added threads to the language. So there still has to be the rule that when the main function returns, the program ends. So that means that when you hit this return statement, all threads get clobbered. But this is a separate notion here. See, this is part of the thread library. This says exit this thread this thread never returns, so the program continues on running. So if the main thread exits, other threads keep running. But if the main thread returns, all threads are killed. So this is another thing that trips people up. There's subtle difference between Java doesn't have this problem because Java was designed from the ground up with threads. But threads were added to the C library many years after the C language was invented. So you have this subtle distinction between thread exit and return. Return and exit don't quite do the same thing in C now. Okay, this return pretty much is the same thing as thread exiting, because that's well, if you call it as a thread. Okay, if you call this thing as a thread, then return and exit do the same thing. If you call this thing as a function, then thread exit does nothing because it's not a thread. Well, I'm not sure what happens if you call this thing as a function and you hit thread exit, it might just kill the program. I'm not really sure what it does. You know, that's why people usually, you have to be careful about these things, because here, this means exit the main thread. This means kill the function. In a thread, I'm not even really sure what's the difference between thread exit and return. And it's going to depend on where the thread is called as if the thread function is called as a thread or called as a function. So it can get kind of complicated. And I actually don't know all the rules for it. Like, I never put thread exit in the thread functions. I just return when they're done. Okay, and that works pretty well. And then you can call the thread as a function or call the thread as a thread. And it's going to kind of behave the same way. But if you mix in a thread exit in there, I'm not sure what that'll do if you call this thing as a function. So it's still technically a thread. You probably then are exiting the thread of whatever thread called this function, which may cause you grief. That may not be what you wanted. So if you call this thing as a function on some thread, and then this function called thread exit, instead of returning to the function you called, it might just halt the thread dead in its tracks, which may not be what you meant. Okay, and that's where bugs come in on this stuff. This stuff can be very tricky, partly because at least in the C language, threads were added after the language was defined. So threads don't really work 100% hand in glove with the language. Threads have their way of doing things, and the language has its, like return is part of the language, it's not part of the thread. And so then this thing has one meaning when you call this thing as a function, and this thing has a different meaning when you call this thing as a thread. And the meaning it has when you call this as a thread is not part of C. It's part of this new thread library, which is added onto C. That makes things messy. Okay, so we have thread exit and we have thread return. At least in C, they don't mean the same thing. This destroys the thread control block. This thing, well, if it's the main method, return means end the whole program. Okay, now let's look at another example. We're gonna skip this one. It's not that interesting. But here's an example of mixing threads with GUIs. Okay, this is a simple little GUI program that just pops up a message box. I'll show you what I mean. Like it's like the world's simplest GUI program. It's a one-line GUI program that pops up a little what's called a message box. Compile it. Now run it. Okay, now the program prompts you for a number. Okay, and it says 0 to quit. So suppose I type in 1. See, I get a little message box. Okay, my number is 1. Okay, now the message box is, the program's blocked on this message box. See, nothing's happening down here. If I click OK, then it asks me for another number. So I'll type 2. Okay, now this is called a modal message box. The message box blocks the program. What it is they're all running on the same thread. So the thread is blocked here waiting for me to click OK. Then when I click OK, I'm back to here. So this is all running on one thread. Then I type another number here, click OK. And if I type 0 here, the program ends. Okay, let's look at the code. I'm in a while loop that's just prompting the user for a number. Then it displays the number in a message box. Okay, here's the function that does the display. Now, notice that I wrote a function to display the number. This function is suspiciously written weirdly. It takes a pointer to void argument and returns a pointer to void. This function was written to be possibly a thread. So this function could be a thread function because it has the interface of a thread function. It takes a pointer to void as its argument and takes a pointer to, it returns a pointer to void. The pointer to void is going to be that, see, it's the address of that number. So then it takes that number, converts it back to an integer, then it creates, then these lines here create the message box. Okay, so this, I need this, this is a little bit of a setup. And then here's the function. This is a Windows function that pops up the message box. Okay, and there's the text, the title, and a couple configuration things. Okay, and then this function returns. Okay, then when it returns, it's displayed the message. Then you can prompt the user for another number. You can scan in that another number, check if the number is 0. If it isn't 0, display it. Notice that the display is just here. Display is being called as a function. So this thing, you call this function that pops up this message box, and Windows, by definition, when you pop up a message box, the box is modal. It blocks until you click OK. So this function, according to Windows, blocks until the user clicks the OK button. Okay. Now I'm gonna launch this message box in a thread. The next example, 9b, mixes GUIs with threads, and what it's going to do is it's the same program. Okay, let me if I open these two programs together, you can see the difference between them. If you look, they line up almost perfectly. The only difference is this line here versus this line here. On the left, display message box is called as a function. On the right, display message box is created as a thread. And if you look carefully, that's about the only other difference in the whole code is that you need to declare this thread ID, because when you create the thread, you need to capture the thread ID. So you need to capture the thread ID. So this function, this program needs one extra variable. So it needs this needs this variable here, the TID variable. That's, so the only difference between this one and this one is the extra variable, and this one creates a thread where this one just calls thread message block. Okay, so now, okay, here the flow of control was one single thread, enters main, prints a message, scans a number, checks the number 0, calls this function. This function does a little bit of work, calls message box blocks until the user clicks OK. When the user clicks OK, this function returns. So this function returns, and then you're back over here and you print another message. So this thing is, this whole function, this whole program blocks while the message box is popped up. Okay. So when the user clicks OK, the message box function returns, which then this function can return to here, then print another prompt to the user, scan in another number, check if it's 0, display the message box. Go down here, pop up the message box, which blocks until the user clicks OK. Now what happens over here? The flow control is the main thread comes in here. The main thread prints a message to the user. The main thread scans in a number. The main thread checks if it's 0. The main thread creates a second thread to pop up the message box. So now one thread is popping up the message box while the main thread prompts the user right away. See, this returns right away. This creates the thread and then returns. So then you print a message to the user, scan in their number. Now this function blocks until the user, notice that this function blocks and this function blocks. This blocks until the user types in a number. This blocks until the user clicks the OK button. So over here, this program could block here and it could block here. It could block forever until somebody types in a number here, and it could block forever until somebody clicks the OK button over here. Here, the main thread blocks on this. The thread I created over here blocks on this. Okay, now if I don't click here, it doesn't matter. This thing's still running. Now this thing will wait for a user to type in a number. When a user types in a number, it'll go up here, check the number's not zero, create a third thread to display another message box. And then immediately print another message down here, scan in another number. This thing keeps, the main thread keeps running here, creating new threads that pop up dialog boxes. Okay, let's run this one. Let's run this version and see how this one happens. Okay, so I need to compile it. Okay, now run it. Okay, so it's asking me for a number, type 1. Okay, now there's the number 1, but look, see, I have a prompt over here again. So I can type in a second number. Now there's 2 threads running. And I can type in a third number. Okay, now there's 1, 2, 3, 4 threads running. Let's call up Task Manager, see what Task Manager is telling us about threads. Now there's 7 threads running. Well, there's these extra threads. There seem to be 3 extra threads. No, now there's 9 threads running. Geez, where'd they come from? We have 1, 2, 3. Now let's wait a little while, see if those threads go down. Let's wait a little while. Now, Windows may be doing something really funny, like this dialog box may be popping up more than 1 thread. I mean, it's hard to know. Windows is becoming more and more complicated as Windows gets to be, oh, now we're down to 6 threads. Okay, now we're down to 6. From our point of view, there should be 1, 2, 3, 4 threads. The main thread and the 3 dialog threads we've popped up. We should have only 4 threads. We got 6. No, so like we dropped from 9 to 6 all of a sudden. I don't know what those 3 threads were, and I'm not sure what the 2 extra threads are now. 2 doesn't seem to make sense when there's 3 over here. If we wait a little, let's wait a little longer, see if that number goes down some more. I bet it will. I have a feeling it will go down. Well, let's launch another thread, and we should see it go up. So, see, now I got 7 threads. I shouldn't have 7 threads, but see, I got another thread. Go over here. Now I'm going to get 8 threads. See, I just popped up another thread. Now I'm going to, now I should drop down. One of my, it went up. There, see, the thread number went down. Now it's going to go down from 8 to 7. See, I'm killing off these threads. But why do I have 7 threads? Where are these extra threads coming from? I don't know. At this point, we have 1, 2, 3 threads. We have the main thread over here and two pop-up threads. So we should have 3 threads. Where the extra 4 are coming from, I don't know. If I kill one of these threads off, see, drop down to 6. If I wait a while, it might actually settle down to 2 threads. Who knows? Windows is just getting, unfortunately, more and more complicated. I remember when I used to do these experiments some years ago, like with Windows 7, it would do what you expected it to do. Now, everything's a little bit off because there's hidden things here and hidden things there that are poorly documented and kind of obscure, which is a problem because when you're really trying to debug real systems, it can be very hard to figure out what should be happening. As the operating system gets more complicated, it becomes harder and harder for people to get their code to be correct because you don't even know what correct is anymore. Like, as far as I know, from everything I know about C and threads, this program has only 2 threads. I have no idea where the C language is producing 4 other threads. They're not part of the C language. The 4 other threads in this program do not come from C, okay? And they do not come from the thread library. They're coming somehow from Windows, but I don't know what they're doing. If this was Java, I wouldn't be so surprised because it's well known that Java pops up a lot, and you can actually find out exactly what threads Java pops up. I don't even know where to look to find out where these extra threads are coming from. Is it part of the thread library we're using? Is the thread library changed somehow? Is it part of Windows? Is it a Windows thing that's made these new threads pop up? I don't think it's the thread library. I don't think the thread, for one thing, I haven't changed the thread library. I'm using the same thread library I installed on this machine it's the same thread it's an old thread library. I have not updated the thread library that we're using. The thread library is this DLL right here. And that DLL is from 2010. That DLL is 10 years old. So that DLL was, that the thread library we're using is kind of old. I just never updated it because, if something's not broke, if it ain't broke, don't fix it. Yeah, and this thread library has been working fine for me. Yeah, so I haven't changed it. So it's an old thread library. So I don't think that's where the new threads are coming from. I don't think they're coming from the thread library. My guess is they're coming from Windows somehow. And we're still stuck at 6. If I kill this one off, didn't drop to 5. If I launch a new thread over here, there it goes up to 7. Kill it off, back down to 6. Okay, but I was at 6 before I killed off one thread and I didn't go down in thread. I wonder if Windows is somehow conserving threads. Maybe Windows threads are supposedly, in some theory, expensive to create and destroy, and Windows might be caching threads or something weird. But then it shouldn't need to create a new thread. Like when I do this, it should need to create a new thread right away if it was caching threads. So I don't know what it's doing. Okay, so there I'm up to 7 threads, though I shouldn't be that high. Now I've got 8 threads. Now, if we used, let me do one other thing. Task Manager doesn't tell you a lot, but there are programs that tell you more than Task Manager. So let me run one of the programs that tells you more than Task Manager. Maybe it'll tell us. So here's one called Process Explorer. Process Explorer, you have to download it, install it, and add it to Windows. This doesn't come with Windows. It's written by Microsoft. It's like a super fancy version of Task Manager. Okay, so it tells you a lot about programs. So okay, there's my program. It's got 7 threads, which is exactly what Task Manager was agreeing on. It's got 7 threads. Let's see if we can find out what those threads are doing. So notice there's things like set affinity. See, a lot of what's in, if you compare that, see a lot of what you see here when you right click on a process, you see a lot of the same stuff over here. But there's actually much more you can do. You can click on properties and you get threads. See, I can actually ask questions about the threads. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 threads. Let's watch the threads over here while we launch. Let's see if we launch a thread and see what happens. Let's launch a thread and see what changes over here. I don't know. Let's see. I'm guessing that this is the main thread because it's got the name of the function, the name of the program. I'm guessing that's the main thread. I'm guessing that those 2 threads are these 2 threads because, well, there's 2 of them. Yeah. MSV CRT stands for Microsoft Visual Studio C runtime. So actually that doesn't mean it should be these because these are not part of the C runtime. These are part of the GUI. But that means that thread is running in that DLL. So that's Microsoft's Visual Studio C runtime DLL. Now this DLL, NT DLL, NT stands for Windows. The original name of the Windows operating system was Windows NT. So they still call a lot of the DLLs NT DLL. So this is actually the operating system. So I have a feeling these might have to do with these guys because these are part of Windows. Let me kill off one of these. oh, one of these died with it. Okay, kill up. So that's strange. This is a GUI prompt, but it says C runtime DLL. Okay, so let me kill off this one. Okay, so now I've got the main thread. The main thread's running, and then there's these 4 threads that have to do with the NTDLL. Now, let me launch a new thread. See, I got that new thread. There's the new thread. There's this thread here. I'm surprised that it's running in the Microsoft C runtime DLL, because this thing's not part of the C runtime. This is part of the GUI. So, good luck figuring out why part of the GUI, Microsoft put part of the GUI in the DLL that's called the C runtime DLL. Okay. And I have no idea what these are doing. I don't know if there's a way to find out. I don't know if there's a way to find out what these guys are actually doing. There's 4 of them. I can't right click on these. I'm right, you can right click on, you can right click over here and get a pop-up window. But in this window, there's no right clicking. There's no little pop-up message. You can look down below. Like, here's my main thread. Okay, it makes sense that it's waiting because it's blocked on. The main thread is blocked on here. The main thread's blocked. And this thread is blocked over here. See, it's waiting. But this thread's waiting also, but what's it waiting on? I have no idea. Now, this gives you the call stack of that thread. For example, this is our main thread. Here's its call stack. And its call stack, that's the main thread. So this should just be the initialization of a C program. Yeah, and again, reading this stuff is not easy. I'm not seeing anything in here that makes me understand what's going on. There's a lot you can play around with here. They all look pretty similar, so I'm not really sure. I was hoping that the call stack would give some clue. Oh, wait for work via worker factory, user callback dispatcher, system service executor. Okay, you can see what's going. You can see these little clues here. System service executor, user callback dispatch, wait for work via. Now, if you Google those names, you might actually find out where they come from. Like, you could take those names and go Google them, and you might actually start. Oh, guess who does this stuff for a living? Hackers. This is how you attack programs. You attack programs by trying to figure out everything they're doing and try to figure out where there might be something you can attack. What does that function do? Is that function a way to attack this program? Is that function some clue that you could use to figure out what this program's doing and a way to attack it? It's called reverse engineering. The people who do this stuff for a living are the people who do what people refer to it as reverse engineering. Try to figure out what a program's doing by watching it and figuring out what was it doing, and then if you could figure out what it was doing, you might be able to figure out how you could attack it. Okay, so reverse engineering is mostly done by hack. It's also done by competitors. Famously, competitors will reverse engineer each other's software to try to figure out what their competitors are doing, and there's some legal gray area in that. But competitors will reverse engineer academics reverse engineer to try to figure out what programs are doing for, and hackers would do reverse engineering. Really hard stuff. Because you can see, you're playing around with tools like this and you're saying, well, what the heck does that function do? What the heck does that function do? Why is it there? Okay. Still don't know where these extra threads are coming from. Notice that by switching to more powerful tools, you can find out more information. Oh, these windows are static. That's another thing. These pop-up windows, some of them, see, there was a refresh button. If there's a refresh button, that tells you that window is a snapshot. So it's not updating itself continuously. So it's only telling you what it saw when you created the window. You need to refresh the window to see if anything changed. So if you see a refresh button, that means the window is a snapshot. You need to refresh it. Now this one is not, this window's live. See, there's no refresh button here. Okay, so this window's live. So that means as I change things, this window updates itself. See, some windows are live and some windows are snapshots, which not obvious. Usually if you see a refresh button, that's the clue that it's a snapshot and that you need to click the refresh button to see something, see more. Okay, so Windows and Linux are full of tools like this that let you dig deep into the innards of the operating system. They're hard to use, and sometimes you can figure out things using them, and sometimes you can't. Still don't know what those extra threads, where they came from. Okay. So, but here, this is kind of a neat, one last thing about this. Let me pop up some threads. Okay, I got a whole bunch of threads popped up. Okay. What happens when I exit this program? Now, let's go look at the source code. Notice that these things are on top. They're modal dialog boxes. So they're on top of everything else. They're supposed to be blocking your program. So it's kind of cute the way they sit there on top of everything. They don't sit on top of each other, but they sit on top of every other window. So if I call any other window, they'll sit on top of it. See, they'll sit on top of pretty much anything other windows. They sit on top of, they sit on top of, it seems like everything so far. Okay, now look at my source code. Look at the source code. And what is this? What happens when you drop out of this while loop, the main thread returns. Now remember, I said returning of the main thread is different than exiting the main thread. Remember the last example we looked at, this one exited the main thread. It never returned, it exited. Oh, if it never returns, why don't I get rid of that line of code? Well, if I get rid of that line of code, the compiler is going to complain that I wrote a function that doesn't return. So even though this line of code is never executed, the compiler will complain if I delete it. Okay, the compiler doesn't know what this function does. The compiler doesn't know that I never get to that function, but this is a function that's supposed to return it. So I need to have that return statement there just to keep the compiler happy. Okay, now this thing exits. Exiting does not halt the program. If you exit the main thread, that just exits the main thread. Other threads are running. But now here, I'm going to return from the main thread. So if I go to the running program, if I can find it, oh, there it is. If I type 0, see, everybody died. All the threads went with it. Now let's change this to, let's put a thread exit in there. Let this guy exit instead of return. That should leave all those dialog boxes still up there. So let's check, let's just try that now. So compile this one, now run it. Okay, now exit. See, now what happened here? What happened over here on the left?
Waiting for threads to finish.
Yeah, so my program's still running. So I have not returned to the shell prompt because from the point of view of the Windows operating system, this program's still running and it's waiting on these threads. Okay, one last thread. Now when I click this thread, oh, I'm goofed up. Oh, I've goofed up the operating system. I've confused the heck out of Windows at this point. Actually, now this is interesting. I've confused the heck out of Windows. The main thread exited with other threads still around, and somehow it seems that my program's never terminating. My program's kind of stuck in limbo at this point. That's actually kind of interesting. The program's stuck somehow. Okay, it's got, well, it still has 5 threads. Whoever, that's the problem. There's still these threads running that we don't know where they came from or who owns them. So that's what's happening. Since I never called return on the main thread, nothing killed off these extraneous threads, and they're still there. So we've still got these extra threads running, and the program's, oh, I'm down to 4 now. There were 5. If I wait, maybe those threads will go away eventually. You can try this at home. Just go let this thing sit for a little while. Maybe those threads will die off as time goes on. We don't know what they are. We don't know who put those threads there or what their purpose is. Maybe they'll die off. When the last of those threads die off, this thing will terminate and we'll be back to the prompt. Now I can control C it. See, I can control C it, but then I'm just killing everything. Okay, so notice that there's weird interactions between threads and windows and the main thread. There's this stuff can get really confusing. This stuff can get to be a mess. The difference between exits and returns and extra threads. Once you enter the world of threaded programming, things get messy. And it's just an unfortunate part of the reason is because a big part of the reason is because C language was not designed for threads. So threads were tacked on to the C language afterwards. Whenever something gets tacked onto a language after the fact, it can make things a mess. Java is a little bit more straightforward because Java was designed from the ground up with threads, but threads are still complicated. They're still messy. Okay, all right, we actually have, okay, so we finished the examples in this folder. So then on Thursday, we'll start the, let's see. We finished the other examples in this folder. So on Thursday, we'll start the examples of what's called race conditions, okay? And if you read the reading of race conditions are explained in the reading. So if you look at this concurrency, why it gets worse, shared data. This is when he starts talking about race conditions. So you read that, make sure you read this stuff because that gives you a background on what we're going to be talking about. So we're going to do not the same example he does, but very, very similar example. We're going to do an example. It's almost just like this example here, but we're going to look at what happens when you have shared data, something called race conditions. Okay. He's got a bunch of references to races, this idea of, well, that's trait. I'm getting the word trait. I want race, but there's something called race conditions. Yeah, see here. There's where he introduces the term race condition on page 10. Okay, so that's where we want to start. We'll start looking at what we mean by a race condition. One of the really important ideas in threading. When you do threading, after you learn what a thread is, the next thing you have to understand is what a race condition in a thread is. Okay. Any question about what we did today? Any question at all about what we've done so far today?
Nothing from my end.
Okay. Try these experiments on your computer at home. Get used to playing with Task Manager. I brought up this thing called Process Explorer. If you just, one last thing, I'll only show you. It's a standard little piece of, it's a standard Windows tool. It's a little download. It's not an installer. If you go to its website, see it's from Microsoft. It's a zip file. You just download a zip file and you can unzip the zip file and run the program. So it's not a big deal. See, it's just a zip file. The Process Explorer is just contain, there's nothing to install. It's a great little piece of software. I mean, I have it already on my computer, but all you have to do is download that zip file, unzip it, and you can double click on the program. It does not run an installer. It just runs the program. So I really recommend you play around with Process Explorer. It's just a super fancy version of Task Manager. Okay, and it's written by Microsoft, but for some reason they don't include it with Windows. You need to go download it separately. Okay, all right. So I'll quit here, and we'll, like I say, on Thursday we'll start talking about shared data and what we call race conditions. Okay, so see you on Thursday. Bye bye.
Bye, sir.